Thanks for the nice introductions. Yes, I'm going to talk about two ESA studies which have been performed at ESMWF by Katie Lee, Niels, Bormann, Sean Healy, and myself, running ensemble of data assimilation experiments using GNSS-RO data, radio occultation data, and microwave sounding data. So this is the outline of my talk. I talk a little bit about the background and how the EDA, the Ensemble of Data Assimilation, is used at ECMWF. Second, then I show you, how the EDA spread, the measure we usually use, changes when we add more GNSS-RO data, and furthermore, I talk about how the EDA spread actually relates to O-B statistics from observing system experiments, both for GNSS-RO and for microwave sounded data. And then lastly, I talk about the EDA spread, how it is impacted by the addition of simulated data for those two data sets. So a little bit of background here, why we actually run the EDA. We do it to estimate the statistical uncertainty in the short range forecast, but also in the analysis. And are you not? Okay. Sorry. Pushed the wrong button. So the configuration I'm using here, or we used actually, is a control run, and then and 10 members. And those 10 members are 10 independent cycling assimilation systems, where there's some perturbations added to the observations, to the sea surface temperature, and to the model physics. And this is a little schematic showing you what it actually means. So in blue, you have the trajectories from the forecasts from the 10 different members, the forecasts of them. And the envelope more or less shows you, and the width of the envelope shows you more or less the spread. So then, in a data assimilation system, you have the observation in our assimilation window. In our case, it's 12 hours. And if you then assimilate them to each single member, you get the analysis trajectory here in green. And then again, you can compute actually the width of this envelope. You compute the standard deviation to get a measure of that. And we call it the EDA spread. And if the EDA spread reduces, we see this as an improvement in the analysis and forecast uncertainties. So what you can do then, you run a different set of EDA, for example, by adding observations. And then the expectation is actually that by adding those observations, the spread in the EDA is reduced, as you can see here, which is seen as a good thing, as I just said, and this is just uncertainty reduction. The EDA is run because it is used in the ensemble forecasting system, because it contributes to the initial perturbations. There are some limitations to the EDA, and it's good to know them because we know the EDA is underdispersive. It's not, that's very common. It also is common for other EDA systems, not just for us. In our case, we actually the raw spread values I'm going to show you in operations, they're increased by 34%, and when it's used in the 4D raw system. And the ensemble forecasting system actually, still requires singular vectors to be added to actually get a realistic spread values. So there are some limitations to DDA, and we know it's not perfect, but it's all work in progress, and it's active research here to make the EDA even less underdispersive. But if we actually assume, going back to the background, that the perturbations we add to the EDA more or less are correctly specified, then the EDA will provide a good estimate for the analysis and short range forecast error uncertainties. So this is just how the EDA spread is computed. It's a normal standard deviation about the ensemble mean. And this is done for each assimilation cycle. And then if we actually average over all the assimilation cycles, we end up with our EDA spread. So not a very complicated equation. So first, let's look into the change, how the EDA spread actually changes when we add more GNSS-RO data. And for this reason, I've run different sets of experiments, a control one, which is like just using the data which is operationally used, including the GNSS-RO data. Then I excluded all of the RO data in blue, and then I added more data from the Cosmic 2 and the Spire constellations. And this was really possible in this ESA study to do it because we had the availability of those two extensive GNSS-RO data sets. And here I'm showing you a plot by Harnish et al., which was more or less the motivation to do actually this study, because he tested how simulated GNSS-RO data changes the EDA spread. Here it is for temperature as a function of pressure. And the different colors just are relating to the different experiments he is running. And, as expected, the more data you add, not larger, the smaller the EDA spread becomes. And the biggest reduction happens in the stratosphere. And the right-hand side is my plot showing you as well for real GNSS-RO data that the spread reduces, especially in the stratosphere, as I said, which is not a surprise for GNSS-RO data because this is the core region. So you can display this slightly differently to really see where the biggest changes are happening as a normalized difference in spread here on the left-hand side, the plot. And if you compare, let's say, our experiment in green, where we have most of the GNSS-RO data, to where we have none, then you have a reduction, for example, 10 hectopascal by 21%, which is quite big. But I have to say the largest EDA spread reductions in this constellation happened in the tropics and in the stratosphere, as I just said, because we did add most of the data in the tropics. So how can we actually use the EDA spread? Because the ultimate goal is to use it to estimate what kind of impact the observation have. And usually when you run normal observing system experiments, you look at the O minus B statistics or the first case departures. So we want to find a relationship between them. And you can go back to theory and say, okay, the O minus B, the variance in O minus B in the first case forecast departures relates actually to the forecast error statistics, sigma B, and also the errors in your measurements as sigma O. And in our case here, we looked at radius on measurements. And if there's no correlation between, sigma O and sigma B. So this is an assumption you have to make. So, and when you remember correctly, we can rewrite this equation to actually say that sigma B is actually estimated by our EDA spread. So you can say the variance in O minus B is equal to a scaling factor times our EDA spread plus a constant. And this constant C should be the variance in our observation errors, in our radius and measurement errors. So this equation we will use to find a relationship between our O minus B statistics and the EDA spread. And this is the plot and some colors, so you can see it a bit easily. So on the x-axis, you see the variance in EDA displayed in red, and on the y-axis, you see the variance in our O minus B. And the different dots relate to the different experiments run, adding more data. And first of all, you see for temperature here in 100 hectopascal in the tropics, the dots really align nicely, and you couldn't run a linear regression through it and see it's a very nice, yeah, as you can see, linear relationship between them. But you might, when you look a bit closer, you see, okay, the values in the EDA variance are much smaller than the values for the O minus B statistics. And you can do this plot for different height levels and for different regions. And this is more or less a similar plot I just showed you, just adding more dots which refer to different experiments. and the color coding tells you how much data is actually used in this case. And so with very little data, with very much data, sorry, on the bottom left is the experiment with the most data, and it does show the smallest variance in O minus B and the smallest variance in EDA, whereas the experiments with less data shows you again the largest values. So you can plot, as I said, for different hemispheres, for the northern hemisphere and for the southern hemisphere. And first of all, you see, okay, the linear relationship is not as linear as it is in the tropics. And then also, if you look a bit closer, the slope or the scaling factor m is different. In the northern hemisphere, it's 8 in this case. In the tropics, it's 5. In the southern hemisphere, it's 10. So it does vary. So just to summarize the finding, this is what I just said, that you see a decrease in the EDA variance, but also a decrease in the first case departure when you add more data. But the slopes are different. Why is it not going? The linear fit is less good for temperature in northern hemisphere, I just showed you, but you can also, do these kind of analysis for relative humidity, for example, and then you do find for lower altitudes 700 hectopascal here for temperature, and you do find it's also, not as good, especially in the extratropics and also in relative humidity. And this could have different reasons, but we think this might be related to the representation of scales in the A, that not all the scales are resolved. But it is an area of active research at the moment to understand the nitty-gritty details here, and to also improve our EDA systems. So this is the plot from Katie's study now using the microwave sounders. And she also shows here the EDA variance versus O minus B. And in her case, she shows here different experiments, EDA experiments using no sounders in blue, for example, and then adding either humidity or temperature channels to the constellation. And you see again, the more data you add, the smaller values you get in O minus B and in the EDA. But when you look closely, especially for radius and temperature at 100 hectopascal here in the northern hemisphere, no, in wind in 200 hectopascal in the northern hemisphere, the EDA spread, the values are much smaller than the values for the O minus B statistics. And again, the scaling factor here does vary, which is just summarized here. But qualitatively, it was really nice to see that for real data, that you do see this relationship. There is a relationship between the EDA spread and O minus beta statistics for microwave sounders as well as for GNSS-RO data. So these findings qualitatively are very similar, but as I said, the details do differ. So let's look at the impact on the EDA spread when we add simulated data. So first, a few words how we did this actually. How did we come up with simulated data, bending angles for the GNSS-RO, for microwave radiances for the microwave sounders. So we take actually the in ISDA and NWP analysis and interpolate the fields to the observation times and locations, run it through an observation operator, add some noise, so to say, some realistic observation errors you would expect, and then we end up with some simulated bending angles or radiances. For GNSS-RO, I've run 2 experiments adding simulated cosmic 2 data here in green and in black, and compared it, the EDA spread to the EDA experiment with real cosmic 2 data. And this is the plot, which again is for the tropics, because cosmic 2 only gives observations between 44 roughly north and south, so I concentrate on the tropics. It's again the normalized difference in temperature spread displayed here as a function of pressure. The blue one is the control EDA, and then the other colors refer to when we add Cosmic 2 data. In red is the one with the real data, and the other two colors are simulated data with different observation errors added. And first of all, you see, all those lines overlay each other, which is nice. So qualitatively, the EDA spread reduction for the simulated and for the real data is very much comparable. Of course, there are small differences because, for example, the simulated data gives larger spread reduction in the troposphere and smaller reduction above 100 hectopascal. And there could be different reasons why in the troposphere we think it might be related to a lag in the vertical error correlation. And oopsie daisy.
About 2 minutes left.
Thank you. So this was a really nice finding for the GNSS-RO that we actually, we see very much comparable EDA spread reduction for simulated compared to observed data. For the microwave radiances, Katie has used and run real EDA experience real, but also with simulated data here, shown in the second table. And there are different constellations, only polar orbiters or 60 degrees inclined, or a combination of those. And if you really want to, read up on this a bit further, I really recommend to read her final report, which just came out yesterday. So, and it's listed in the references. And she added like only humidity and temperature channels to see the impact. And this is more or less the last plot I'm going to show. It's quite a busy plot. So what it shows you is the reduction in EDA spread on the y-axis versus the number of sounding locations on the x-axis. And the reference one, the 0 line here, is where we have no microwave sounders at all. And the quantity here in this case is the geopotential height in the northern hemisphere at 500 hectopascal. The black dots refer to experiments which have temperature and humidity channels assimilated, whereas the red colors refer to humidity-only experiments. The solid dots here are the ones with real data, and the other symbols are from the experiments with simulated data. So what you first see that, the slope in H-only experiments is smaller, so you have less impact when you only assimilate humidity, and a bit larger when you add temperature. But she does write here that the benefit from humidity is possibly underestimated. So just maybe because of the resolution of the EDA spread calculation and furthermore. But you also see that, the experiments with the real data really align nicely, the spread reduction with the EDA spread reduction of the simulated data. And more or less, the more data you add, the larger is the reduction. But the rate of the spread reduction does slow with more observations. Yes. So to summarize, first of all, we do see that the radius on departure statistics align with the changes in EDA spread, but there is an absolute underestimation when it comes to reduction in EDA spread compared to the O-B statistics, both for GNSS-RO and microwave radiance measurements. For GNSS-RO, we found that the decrease in EDA spread and temperature for real GNSS-RO data was quite nicely aligned with the simulated values found by Harnisch et al. In 2013, even though we have to admit, Harnisch did use a older model cycle, and at this time not as much observations, or the rest of the observing system were assimilated compared to now. But we also found that in our study that the real and simulated Cosmic 2 observations show a similar impact on EDA spread, which is a very good signal that we can actually use the EDA spread as a measure to estimate the impact of real data. And for the microwave radiances, in the last part I just showed you, there was continued reduction with adding more and more data, but the reduction here did slow, especially for humidity. And what I didn't show is there's actually a benefit for wind as well when we add temperature. So yeah, thanks for your time, and if you have any questions or if there's time, let me know.
Thank you, Katrin. Thanks for the great talk. I think in the interest of time, maybe we'll have one question I'll read from the notepad, and that question comes from Takeshi Enomoto, who is asking, is it possible to explain why the O minus B variance and the EDA squared relationship looks linear for relative humidity, which is a nonlinear function of temperature and specific humidity?
Why it does look linear or not linear?
He asks, whether why does it look linear, although there is no linear relationship between these variables?
Well, what we compare here is the EDA spread or the variance in EDA of relative humidity with the O minus B statistics in relative humidity. So according to this equation here, there should be a linear relationship if, if all the other assumptions are met. If there's no correlation between sigma O and sigma B, if the perturbations are realistically added and so forth and so on. I know that relative humidity itself is not a linear variable, but the relationship between those two measures, if everything is met, should be linear.
Okay, maybe I'll take the other questions as well, since like we may have a little bit more time. The second question is from Jianyu Liang, who is asking, do you simulate the GNSS-RO and MW sounder observations in the cloudy region? Is it difficult to get the observation operator for GNSS-RO in the cloudy area?
We do assimilate the data in cloudy regions. GNSS-RO is mostly sensitive to temperature, but also to humidity. But it's an active signal in the L band, so 1.5, 1.2 gigahertz. So yeah, maybe this is more related to microwave radiances, because we do assimilate. They are more sensitive to clouds and so on, but we do assimilate them as well in cloudy regions, which makes it more difficult, to this. If you want to know more about that, you have to read Katie's report, because this is more the complication of here to have realistic observation errors when you do the simulated microwave radiances, that you have there are all sorts of things you have to take into account, which is a bit easier, I have to say, for GNSS-RO data.
Excellent. And the last question is from Tobias, who is asking, what is the reason for the large stratospheric impact as opposed to other parts of the atmosphere?
It's just where the GNSS-RO is, most accurate, more or less between 8 and 30 kilometers, roughly height. We usually say impact height. So this is where the core region of the observation is of the GNSS-RO observations, and yeah. But we do have an impact in the troposphere as well, but it's not as big. But it's just the nature of the observation.
Thank you, Katrin. That was an excellent talk, and thank you for answering all these questions.